This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Good morning. In the last lecture, we discussed about the importance of negative feedback, because negative feedback is very important when you are using operation amplifier as an amplifier. Because operation amplifier, the name is operation amplifier, then you buy the operation amplifier, then you are making your own amplifier using operation amplifier based on your application. And the negative feedback is used in the amplifier. Then we said in the last lecture there are a couple of important parts for a negative feedback system: feed forward system, sense mechanism, feedback network, and then here is a comparison mechanism. And then we said when you have feedback, what happens is your input is no more x, because x is your input in the open loop. But when you have feedback, then your error, that is x minus xf, because this is x, this is xf. So that will be going as the input to the feedback closed loop system. And maybe I will draw it so that we can catch up quickly. So in the feedbacks, maybe this is an amplifier. So here we are learning feedback from electronics point of view. So you design an amplifier with gain A1. Then this is your input, this is your output. Output is Y, X is the input. So then this is called open loop. So in the open loop, your Y by X, and then that is a gain which is equal to A1. That is the open loop gain. But then here your input is X and then output is Y. But then when you have a feedback, what will happen is A1, and then when you have especially negative feedback, then this is your X, and then this is positive, this is negative, because this is a negative feedback system. And then this is a feedback network, and then this is the output. So your output is still Y, but then this is a closed loop operation. And then in the closed loop, you got two gains, A1 equal to open loop gain. See, here also is A1, open loop gain. So open loop gain means you can't change it, because you put all the resistances, you can't change it. And then, but then here you got another gain, that is Y by X. Here Y by X is closed loop gain. See, because now the input to amplifier is not X, it is X minus XF. If XF is a feedback network, if XF is the signal coming here, then X minus XF, that is your error signal, that is going to the input of the amplifier. So Y by X is called a closed loop gain. Then we already derived an expression which is equal to A1 by 1 plus K into A1. So we got an expression closed loop gain in terms of open loop gain. And then you can vary your gain. So this is a closed loop gain. This gain you can vary it. You can maybe get 3, you can maybe get 5, 10, depending upon the application. Then you have to vary this K. And then in the amplifier, how do you vary the K? Because in the amplifier, so equivalent of one is, this is an operation amplifier. And then here you got a resistor, then you got another resistor. So this is your X, this is your Y. And then here is, this we can say at XF. And then this R1, R2. So what is XF? Y into R2 by R1 plus R2. So what is K? How will you find out K? K equal to XF by Y, because that is a feedback constant. So how much you will get it? R2 by R1 plus R2. See, so that is equal to K. So by varying R1 and R2, now you can get your required gain. But op amp got one gain, that is an open loop gain, that is a very big value, maybe 10 to the power of 5. That's a big value. But then you are not using that gain actually when you design an amplifier using in the closed loop. Then your gain you are adjusting using R2 by R1 plus R2 using this feedback. So we came up to that point, and then we took this as an example. That's what I discussed now. So here what we will do is you can vary the closed loop gain y by x, and then A1 is fixed. A1 is fixed by using different R1 and R2 combination. You can get a gain of 5, gain of 10, whichever gain you wanted. Then you also discussed in the feedback system, we derived it. Error signal is an input to your new amplifier, which is equal to x minus xf. But xf, the feedback fraction, equal to k times your y, which we already discussed, which is equal to k into y. And then your y, what is your y? Y equal to error into A1. Error equal to x minus xf into A1, that is your y. So that is the reason x minus xf into A1, which is equal to k into e into A1, because e is the error signal, that is x minus xf. So I can rearrange e equal to x minus k e A1 into x, so that I can get e in terms of input. So e equal to x by 1 plus a into k. So from this you can understand your error signal. So what is the meaning of this signal? So as I said, now the input to the amplifier is error signal, not x. Is it a problem? Because previously in the open loop system, your input is x, but now your input is not x, it is error signal. Then somebody will ask you, so maybe here you are connecting a signal like this, so your output is amplified. But then here some signal x is here, and then the problem is here the input is actually not x, here the input is error signal. Then somebody can ask you, in the negative feedback, are you sure this signal is going as here? Then what will you say? So now I have not connected the feedback, it is open. Then what will happen? This will be amplified times A1 and it will come here. Do you agree with that? Then you are taking a fraction, maybe this is an example, good example. So this one here, and then it is amplified here, then you are taking a fraction here. And then the error, so that is the one that is going inside. So because this minus this will be going inside. And then error, if the error signal is approximately equal to 0, if we can bring that error signal approximately equal to 0, then from this expression what you see is, that's why we derived this expression. If we can make error signal approximately equal to 0, then your x approximately equal to xf. You know what I meant? Means the feedback signal will be kind of a replica of your input signal, so that your error is minimum. In that case, you are getting yes, this same kind of this is a signal, this is a signal, then the error signal is very, very small and it will keep the same shape. So this is a good feedback system. So as A1K increases, error between the input and feedback signal decreases. Because why? Because when A1K is very, very large, your open loop gain is, if it is infinity, what will happen? E equal to x by infinity, which is equal to 0, so your x equal to xf. Means your feedback signal is exact replica of your input signal, so that the error also will follow the same trend. Means when you minus two signals, if both are not in the same shape, what will happen? You may get some glitch. You know what I meant? And then that will go as the input to the amplifier. So you don't want to happen that one. So in order to make your feedback system very good, means your this signal and then this signal should be xf, should be same in the sense the shape wise, not amplitude wise. So this xf should be a replica of the input signal. Otherwise what will happen is your error is minusing x minus xf. So if both are following the same trend, the error is going as the input, so that your input, that trend is followed to the amplifier. But if it is not, what will happen is you may get distortions. So which we already discussed. So if this is the input signal, your replica also should be same signal. If you got a distortion here, what will happen is when you take the minus error signal, that is the distorted signal will be going inside. So that is the reason you need very high input impedance, A1, very high, so that your error equal to 0, error equal to x minus xf. So error equal to x by 1 plus A1 into k, we derived in the previous slide. Then k equal to xf by y. which we already know from here. So R2 by R1 plus R2, I derived it using the document camera, and then KA1, which is equal to R2 into A1 by R1 plus R2. So if KA1 tends to infinity, so if this value tends to infinity, what will happen? Your error equal to 0, because if KA1 tends to infinity, your error equal to 0. When error equal to 0, what is happening? X equal to XF. So when X equal to XF, then we can write your X equal to, because now KA1 tends to infinity, then you can write, because your XF, what is the value of XF? XF equal to, what is the value from here? XF equal to Y into R2 by R1 plus R2 from here. Then you can say, now your X equal to XF. So you can write the X also equal to XF, which is equal to R2 by R2 into Y by R1 plus R2. So if you get to this equation, the advantage is, then you can say Y by X, my closed loop gain, which is equal to 1 plus R1 by R2. Means this is a closed loop gain. So that's the reason in the operation amplifier, this is a non-inverting, because you are connecting your signal to the positive terminal. See, here there is no phase inversion. If you have positive here, it will be positive here if you are connecting to the positive terminal. So that is the reason here you will find some expression like this, V out by V in, here V out by V in, which is equal to 1 plus R1 by R2. Closed loop gain you can vary by varying the resistances. That's what I discussed using the document camera in the beginning. So loop gain, then when you have a feedback loop, people often talk about the loop gain, just the loop gain. What is the gain in the loop? Then loop gain, how will you find out the loop gain? In order to find out the loop gain, usually what people do is just break one point in the loop anywhere. It could be here, it could be here, it could be here. So they break one point, then they ground the input. Then what they will do is they will connect a test voltage source here. Then they can find out what is the loop gain. For example, here see this one, what I did is I broke this point, then I grounded the input, then connect a test voltage source, V test, and then now when you have this as input, we will take this as output, because here you break it, one is input, another is output. And then here what is happening? So if you go to V test here, what is the voltage here? V test into K, that is a, so connect a test voltage source, then your input, then what is your input here? That is equal to 0 minus K into V test. Then what is your output here? Yeah, that is a Vn, that is output, which is equal to whatever the input here, that is a minus K into V test into A1, because that is a gain. And then what is a loop gain? So loop gain equal to Vn by V test, which is equal to K into A1. So that is a loop gain for this negative feedback loop. That's why we find out. When the input is grounded and the loop is broken at an arbitrary location, the loop gain is measured to be K into A1. Excuse me. So this is Vn by V test, that is a loop gain. Then we can also break it some other point, because you broke here, you can break some other location. And then now what I am going to do is I am going to break here, this point, because as I said, you can break here. So you broke previously here, see that's the reason here. Now I am going to break here the point, then I am going to connect a test voltage source here, and then ground the input. So I grounded the input like here, but at the moment what is happening is here you are breaking, and then you will be connecting, because amplifier is operating in the clockwise. You know what I meant? So that is the reason we are not connecting signal here. Amplifier is not working like this. Amplifier is working, signal is going like here, then coming, feedback signal is coming like this. It is working clockwise. So that is the reason when we break here, we will be connecting signal here, because signal should go to the amplifier input. And then when you break here, then what is the result? So what is Y? V test into A1 is a Y. And then what is here, output here? Yeah, K. And then what is here? N. Yeah, so again 0 minus K A1 into V test. And then Vn equal to minus K A1 into V test means again same result, minus Vn by V test equal to K into A1. So you can connect, you can break here, or you can break even here, or you can break even here. Now somebody might do like this. Here what we did is previously you broke here, then someone broke like this, and then we connected signal here, and then this was output. But then somebody did other way around. They did the same thing. Everything is proper. They grounded the input, but then they connected the signal here. This they have taken it an output. Will it work? What is the problem with this? So you go to your transistor amplifier, you connect a signal at the output. Will you get something as the input? Or you got an operation amplifier and then you connect your signal at the output. Will you get something in the input? Take simple transistor amplifier. So you are connecting signal to the collector, then you are going to measure something in the base. Will something come? You won't get anything, because usually the amplifier, all the circuits are designed in such a way that output to input nothing will go. Only input to output signal will propagate. If something propagates into the input, means then your device is faulty. So then you can't pump signal from output to the input. So then this one will not work, because what you are trying to do is you are connecting signal to the output, you are pumping signal here as an input. Your output now you are using as an input, and then you are trying to use it, but you can't. Signal will not go from output to input. So this way you can't get the loop gain. Incorrect calculation of loop gain, because this is logically not possible. So that is the reason when you break it, you have to connect your signal here, because then signal will be going and then it is going to the input of the amplifier and then coming out. Even when you break it here, we are connecting signal here, because signal is going to the input, not here. Signal is going into the input of the amplifier and then coming here and then like this. Signal naturally flows from input to the output of a feed forward or feedback system. If we apply the input the other way around, means to the output, the signal we get is not as a result of loop gain, but due to poor isolation. So in the amplifier or in operation amplifier or any other electronic device, usually signal will not go from output to input. If it happens, your device is faulty, there is no isolation. There is a proper isolation between input and output. I think that is all the examinable part for the subject. And then now what I will do is, you all are already familiar with the mid-semester test paper, and then the same way we will be preparing the final exam. So you will be giving a booklet. In the booklet you will have space, and then you will be writing your answers. Pretty much similar to mid-semester test, you may have more questions from other topics. And then there will be a formula sheet at the end. Only the required formulas will be given, so that you don't have to spend much time going through the formula sheet. And then you know that, okay, from that you also get some clue in the sense, okay, these formulas will be used. You know what I meant? If you need any other formulas, I will be there, you can ask me. So if you ask me one formula, I can give you maybe 5 formulas. Yeah. And then I will show you some examples. I think maybe you got some question.
So it's like the RL for the connector. So
Which one? Which one, sorry?
This is the output and from collector. Looking in like the RL of a transistor. Because that's like 1 plus EM bracket.
No. That we will not provide, because if required, we will tell you derive the expression. You know what I meant? But the standard equations will be given, but we will not give any input impedance or output impedance. If you don't have to derive it, we will already given in the question paper. Assume that this impedance equal to 1 by GM parallel R or something like that. Yeah, I will see. So the lab deadline I have extended, so that you got more time now, because I don't want you to be in hurry and to submit without understanding. So you got more time now to submit. So this is an example from the last year, because we are not supposed to give any numbers about this year. So this is from last year, the syllabus. If you look at the questions, around 46% questions were from BJT, CMOS and amplifiers. Because which makes sense, because most of the lectures are on BJT, CMOS and amplifiers. Then current mirrors and differential amplifiers. Again, that is a big chapter. So that was around 36. Then frequency response. These are the easy marks. See, 12%. You got only 2 lectures. Feedback, couple of slides, you get 6%. So this was the distribution from last year. So we will be, following maybe pretty much a kind of same distribution, maybe a little bit variation, but kind of, this was our distribution. Why we came up to this distribution is based on the number of lectures and importance of the topic. We take both into account. Then if I were you, I will study definitely frequency response and feedback. In 1 hour, I already got to see around 18% of the mark. It seems you get more marks, because this one you already got 18. If you got mid-semester test another 10, close to 10, you already got 28%. Then if you got lab marks around 20, then you already got, my goodness, 40, 30, I think how much? 48. Seems you all will might get H1s. And so this is roughly we are not randomly setting the questions. We carefully think and then set the questions. So this was pretty much there will be big 4 questions. This is from the last year. Again, there will be big 4 questions this year. We follow the same trend. So there are total of 4 questions. Then please don't think that only 4 questions. Each question got subsections, like maybe 3 subsections under question number 1, another 3 subsections under question number 2. And it's a closed book exams, and the questions are set for like 70 marks, because 30 marks, 10% from the mid-semester test, 20% from your lab, and the remaining 70 from the final exam. Then calculator, please note that in the exam venue, they will not allow you any other calculator other than FX82 or FX100. So usually they put FX82, but then I put one more option, FX100, because if somebody got FX100, you can bring it. But then please don't bring any other calculator. They will just remove it. So please bring FX82 or FX100. And then, as I said, you are instructed to answer directly on the exam paper itself, because you don't need to bring any extra paper. We will provide you the space.
Are we given the book, or are we writing on the...
No, for the like mid-semester test. You got the question, and then you got the space for writing the answer. So you don't have to bring anything except to your pen, and then bring your knowledge with logic. So I would say not your knowledge. Bring your knowledge and apply in the light of logic. That's all you need. Then exam preparation. So exam preparation, I would encourage you to go through the lecture notes. Then the group activity, the problems that we discussed. Then we have got problem sets 1 to 5. So please go through those. And then there are some LMS online quizzes from 4 sections. So if you already done all these by this time, then what will you do? Maybe you can go through some problems in the Rasavi's textbook, if you have done all these things. So these are the important things. But then if you already done this one, please go through some problems in the back of Rasavi's textbook. And so the problem sets, please try to understand. As I said, please don't sit down and then see the question, see the problem, answer, see the question, see the problem. Everything is fine, but then when you are in the exam hall, you will get stuck. If you are, so what I will do is I would recommend you to be getting the question, think about the question, then you try to do it yourself. Then you might get stuck. Then please don't look at the answer. Then go to the lecture notes and then see, understand things, and then again try. Again, if you are getting stuck only, you look at the answer. That is the way you should be preparing for exams. Because I did a mistake when I was a student, and that was not the final exam. So that was kind of a mid-semester test. I prepared because there was some big party and all going on. So when I checked, everything was easy. Oh, the question answer in the one day before. Question answer, everything is fine. But when I sat down, started deriving, I got stuck. Then I thought maybe next question will be good. No, next question also I got stuck. So based on my experience, I'm telling you, please work out by yourself. When you get stuck, please don't look at the answer. Go to the relevant syllabus and read the sections and again try. Again, if you are getting stuck only, look at the answers. The quizzes I would definitely recommend because that will definitely enhance your knowledge. So that is the reason I have asked some people to prepare the quiz and post it on LMS for you. And as I said, the students are instructed to answer directly on the exam paper, your question. So like, question is like this, then you have to write your answer here. Then again, the formula sheet. The formula sheet is something like this. You will be provided all the formula, collector current, transconductance, output impedance. Here you asked the RO is here. And then, but we will not give you 1 by GM parallel RO. But you don't need it, you know that one. Then, but please don't ask me, what is this W? What is this mu? And that only please don't ask. And you should be familiar with those terms. And GM, or you should not ask me GM, what is my GM? So, but you should be familiar with this equation. IC is collector current, VT. Obviously, if you don't know, I will definitely tell you. But that is not advised. So there are some extra consultation hours, and I will post it on LMS. I don't know when you want the consultation because the exam is on 20th. And I don't know, because your exams are kind of not all the people are attempting all the exams, so your availability is kind of not uniform. So what I'm going to do is I will give you 3 hours of consultation next week. Okay, so if you have any questions, you can come and see me. And then if you have questions later, you can email me. So when you email, please make sure that if you are sending me some photos of some derivation, that you can open it. It's a big size, sometimes I won't be able to open it. So you please make sure that everything is written clearly and so that I can answer to your questions. So please avoid sending any questions on 29th night because 19th night because your exam is on 20th. So if I get 19th, I get so many because we got 250 students. We get so many emails. I get your head tutor's help as well to reply to your emails. I know that I will get some emails on 18th, that is fine. But 19th night, if we get so many, then it might be not useful if we send it in the early morning because exam is in the early morning. Because I think last year or year before, the exam was in the afternoon, 1:30. Then we got email until 11 a.m. But then your head tutor and I sat together in my office and we replied to all the emails. But then I don't know whether it was useful because we replied it to someone at 11:30. But the exam was like 1:30. Maybe you may have, if you send it, at least what I would understand is at least then if I am sending the question, I got the answer. The only thing I can understand is, okay, at least this can be solved. Because you won't get time to go through it. Yeah, so maybe please send me the questions maybe by 18th if you got some questions. Even 19th is okay, but not in the midnight because you got the exam in the early morning. Yeah. No, I usually get it. That's the reason. I want to be replying to all of your emails because I don't want to losing your mark because I did not reply to your any email. And also please send me from your university account because some of the letters because you got some foreign account that will push it into my junk email. Because recently some of you got some emails from me because I was checking my junk email, then your question went to my junk. Because of that some special characters, it went to, the junk and then I replied. So for the exam, please don't take, that risk. Please send me from your university email ID, not from your personal one. Sometimes if you got some special characters, it can push to the junk folder. And then I will post the exact time for the consultation. And otherwise, I thank you for learning the subject because that is a more important thing. Because I should be thanking you for learning, and then I hope you enjoyed the subject. And then having said that, I am not finishing here because I got 15. No, it's only 11:45. I got some more time. Then I want to teach you about a little bit more that is not examinable because examinable part is already over. And so what I am going to teach you is related to virtual ground in the operation amplifier, because maybe that is an important concept. So I will just tell you, but that is not examinable, because I think as an engineer, electronics engineer, you should be knowing what is virtual ground. So virtual ground means you will hear when people are designing operation amplifiers, you may see this is operation amplifier, and then you will be having this operation amplifier. That is this is in the open loop. So when you are operating in open loop, as I said, we can't connect a signal in the open loop. When you connect a signal here, this one got around gain A1 around 10 to the power of 5. So if you connect even a very small signal, this will saturate. And even if you ground it and then you connect a signal here, so you can't operate your operation amplifier in the open loop as an amplifier, because you connect even here microvolt, still it will saturate. Saturate means if you are connecting plus 5 volt rail, minus 5, it will hit the plus 5 during the positive cycle. You can't get the amplification. That is the reason we operate in the closed loop. And then in the open loop, we use for comparator. There is an application, comparator, which I discussed in the previous lecture. So when it is in the closed loop, you have two ways you can operate. One way is you connect your signal to inverting. Another way is you connect your signal to non-inverting. So this is negative, this is positive, this is positive. So this is called non-inverting amplifier. So non-inverting means you are connecting your signal here. If you got a signal like this, there is no inversion in the signal. Inverting means you are connecting your signal. So this is a signal. And then here, if you are positive, then it will be negative here. So that is the two ways you can operate. Then non-inverting and inverting, the difference is in the non-inverting, you are getting a resistance here, then you are getting a resistance here. In the non-inverting, you might be having some resistance. So that's a different way of designing. So you will be having a resistance here like this, and then maybe you have got another resistor here like this. So you will see non-inverting, and then maybe you are grounding here. So this is an inverting amplifier, this is a non-inverting amplifier. And then, so when you look at non-inverting, so this is non-inverting, this is called inverting. And then, so you will find two types of designs, inverting, non-inverting. Then people will ask you what is the difference. In the non-inverting, obviously the reason is here also you got negative feedback, see. This is an amplifier. The difference is in the non-inverting amplifier, your signal is coming here, but then the signal got very high impedance. Your input impedance is very high. You know what I meant? Because input impedance of operation amplifier is very high. But non-inverting, what will happen is, non-inverting, your impedance is kind of this one. This both will be affected, not the input impedance of operation amplifier, because you already got a resistor here. So in the non-inverting configuration, your impedance is less, input impedance is less. Then people often talk of something called virtual ground. Virtual ground means it's an interesting concept. Operation amplifier in the negative feedback will try to make this signal equal to this signal. It will try to match it. So that is a very interesting concept. That's called virtual ground. I did not initially understand the concept of virtual ground, rather than understanding, okay, this point is virtual ground. It's like this point is virtual ground. So this point is a virtual ground because this is ground. So this point also is a ground. So that is a virtual ground. Then, but I didn't understand the key way of understanding the concepts. So I struggled a little bit when I designed some amplifiers, especially when I wanted to debug it. But then later I understood the concept. That made me more confident in operating with operation amplifier. So what is a virtual ground? Virtual ground means, as I said, the operation amplifier will try to match this signal and then this signal. Inverting and non-inverting almost same. So that is called virtual ground. Then for an operation amplifier, your V out, which is equal to A1 into V positive minus V negative. This signal minus this signal into open loop gain. So that is equal to V out. Then I can say V out minus V minus, which is equal to V out by A1. Do you agree with that from that expression? Then if A1 tends to infinity, what will happen? then this will become 0. Then what is the meaning is V plus, which is equal to V negative. Means if you design an operation amplifier with the A1 very, very high, operation amplifier always try to pull this voltage equal to this voltage in the feedback. Then, so that is the reason here you have got a ground. So operation amplifier will make sure that this point also is 0. But then this one you have not connected 0, but then this is a virtual ground. It's called a virtual ground. And then that concept is coming, then people will ask two questions. Why are you getting the property of virtual ground? Then you can write down the equation V out equal to A1 into V positive minus V negative. If A1 is very, very high, then V positive minus approximately equal to V negative, because that is the reason operation amplifier A1 open loop gain is very, very high. Then that also you can get understanding how to amplify the signal. See, now what I am going to do is, you got this one, and then I can show you some interesting way of understanding the operation amplifier gain. So I am going to get a negative non-inverting amplifier. So here I am going to have 1 volt signal. What I will get here is a buffer. If this equation, if this is correct, A1 is very, very high, then operation amplifier will make sure that V positive equal to V negative. So if this is 1 volt, this will make sure that this also is 1 volt. Means here you get 1 volt signal. Now what I am going to do is, I am going to connect a resistor here. I am going to connect a resistor here. This is 1K. This is 1K. Now what is the gain? This is 1 volt. Then operation amplifier will try to make this 1 volt. Do you know what I meant? If this is 1 volt, this is equal to 1 volt. Then what will be this volt? 2 volt. See, now you are getting an amplification. So that is the reason your Y, your X. So that is the reason Y by X equal to 1 plus R2 by R1, the expression we have shown. And then which is equal to 1 plus R2 by R1. What is R1 equal to 1K, R2 equal to 1K, 1, which is equal to 2. See, you are getting gain 2. So now you don't need the equation. You can, conceptually you can understand. You can find these equations. Without understanding, using this virtual ground, you can amplify the signal. You know what I meant? So that is a concept of virtual ground. So using the concept of virtual ground, whatever we discussed, see, this is a gain we derived in the slide, but without this equation, still, we can find out the amplification. Anyway, this is an introduction to ESD, electronic system design. We will be, taking off from here. But then I thought I will introduce this one because as an electronics engineer, this is an important concept of virtual ground. So in the syllabus, then what we have covered is we studied the small signal response, because that is important when you design the chip. You are designing using cadence or whatever the circuit you want to design, that is important. Then we have taken LM741 as an example so that it makes sense. These are the blocks you used in the LM741. And then now you learned how to design the amplifier, how to design audio amplifiers, then small signal responses, which is very important when you design integrated circuit. And another thing is you got a very good hands-on experience with analog discovery. Then at the end, you can design a small operation amplifier from discrete components at the moment. And then you also learned that operation amplifier you take as a black box and then design some other amplifiers using operation amplifier. So these are the expected outcomes from this subject. And then how much you learned, how will you know? How much you learned is you can think. When you came for the first lecture, if you are coming for the first lecture now, no, I'm not talking about my first lecture, and then now you think now where you are, just to minus it, whether you learned something, these things, whatever I discussed, whether you learned or not. You know what I meant? So how much you gained at the moment, how much, where you are previously, where you were, and then if you got a difference, then you have learned something. If you haven't got any difference, what will you do? No option, you have to attend my lectures maybe next year. So then I think that's all, and thank you very much. So I will post my consultation hours on LMS today evening. Thank you.
That's fine. It's very, very fancy.
Yes, it's different from ours.
A little bit different. Okay.
That's interesting. You have it connected to the...
Where is it? Yeah, so the PDF that I sent to you has just a picture of the video. So
I
those,
think it's okay.
yeah, it's a,
Normally, these kids, they want it to be online a day before so that they review it before.
they can determine whether they want to turn up or not. Yeah, that's okay. Now, actually, one question: Did you guys talk about you know, the different windows for transmission?
Yes, yes.
Okay.
I think this is shown multiple times today. So they know about
okay, so no,
the
okay.
fiber, they
Okay,
know
great.
where's the windows.
Okay.
Yeah. I think it's a good division.
Have they looked at
Yeah, they know about this.
the metastable states?
Yeah, and they wouldn't. They know about the game, but I didn't go to that detail in terms of what's the impact.
Yeah,
of
okay.
it.
Have you talked about C-band and L-band?
Yes.
And
Just
how L-band was made in terms of very much longer lengths and lower inversion?
no.
Okay.
No.
I might mention that just to give you a little hint.
They know about C-band and L-band.
I assume you haven't seen something like
yeah,
this.
this is good.
This is really cool. I know. That's what I like to see.
I just tell them that it's in a box.
Yeah,
That's
yeah,
about
yeah.
it, but not inside there.
Yeah, and so the other interesting one,
Yeah, for the Raman, that's good because I haven't told them how you do Raman.
Yeah,
multiple
for
channels.
WDM,
I just know
yeah.
just one channel, how you do it.
yeah. So the
This is,
so
they
this
haven't
is
seen
kind of
this
new,
before.
right?
Not Rodem. Yeah,
Okay,
not this.
okay, that's cool. So I'll spend a bit of time on this. I mean, I don't really have that much because I'm not really an expert in this. I mean, I'm a user, right? Just like you. But for the channel monitoring,
Yeah.
I can spend